Hey, this is How I Resolved Time Dilation, Episode 2, Part 2. And I want to start off by clarifying that I mean relative lengths of time and not just lengths of time in general, because at the beginning of Part 1, it kind of sounded like I was implying that all lengths of time were equal, and that's not at all what I'm saying. I mean that all relative lengths of time in comparison to each other, like like in a setup of relativity, like you have a stationary observer and a moving observer. That's it. Um, and here, where I say 0 points are not always arbitrary, all I mean by that is, like, if you had a stable equilibrium, like imagine a parabola, you wouldn't put the 0 point on the side of the parabola. It just wouldn't make any sense. Like, it has to be at the bottom. So there's like some cases where equilibrium is a certain point, and I believe that equilibrium in time is at the speed of light. And it's just interesting to consider the similarity of how light first thought to be a particle, was discovered to have a wave nature, and that's what we're going for here. Um, Further clarification: the lines coming off here are obviously, like, that's the direction that time would be going in at that moment. But then taking the derivative along the curve that's created from all of these instantaneous directions that the moving frame was going in, it's, I realize that that's not the same direction that time was going in. Like, the derivative here at the top is going straight across, like parallel with the primary axis, but that's not the direction that time was going at that point. It was actually going off in this direction. But nonetheless, it's still the case that if you assume that relative lengths of time have to be equal, and if you let time be in 2D, and we're representing the moving frame with a longer length of time, then it's just only natural that the rest frame has to have a longer length of time in it as well. We went through that, and again, all of these, it's like a continuum. These are fundamental loops, or chronons, or whatever you want to call them, but they're rotating in unison, and the so the trick that's used here classically to get time on the sides of the triangle to begin with is to let x equal vt at rest, or like with no acceleration, because that's like the simplified version of x equals x naught plus v naught t plus 1/2 at squared or whatever, just no acceleration. But then so whenever you do that and you get time on these sides with c normalized to 1, the only difference then between here and here, besides using k delta t for this leg instead of vt, is like, you have an extra dimensional inconsistency here, where it's like you're multiplying by 1, you're multiplying by 1, you're multiplying by a fraction of 1 here, and the only thing keeping this extended in physical space and not in a two-dimensional hypothetical time field is the fact that there's like a 1 with dimensions of meters per second off to the side that like switches it back out and makes them meters instead of time. But then if you start from the other direction, like that's trying to deconstruct or trying to like reconstruct the classical triangle into the time equilibrium triangle. But if you start from the other direction, you don't have that little meters per second off to the side there, because we're just treating velocity implicitly. Like we just kick it off. It's not even being used to begin with. You just have two equal lengths of time. You have the projection coming down. We use our K method, K times delta T, and of course the hypotenuse is always going to be longer than the base leg here in a triangle, and that means that delta T is always going to be non-negative, and whenever V goes to 0 in the moving frame, this collapses. So like it's just a timeline. Like that's totally consistent with like even pre-relativity. Just time is a line, like one-dimensional line. Well, it adheres to that. My triangle, and then of course, what this means, you might be scratching your head, but what we imply here is that since the lengths of time are actually the same, but the loops are expanded out, and there's less opportunities for physical change to occur in the moving frame as a system. So what we say is that there's less system evolution over a set or equal length of time. So the path through the time field is dilated, and less change happens because, you're actually going, or like less physical, that's just it, less physical change is able to occur, because, you get it. And so we hope that this isn't a begging the question here. We've tried to avoid a begging the question situation, because I realize that you have to assume that there might be a time field, or that there is one, to see whether it might make sense or not. But we're not either explicitly or implicitly trying to say, time field is true, therefore it's true. We're saying, if you assume that there is a second dimension of time, that it's consistent with the classic. If our assumption that a second dimension of time exists, if that assumption is consistent with the classical setup, then that gives credence to the assumption. And the assumption is consistent, therefore the assumption gains plausibility. I'm still not sure, but because I don't want to be making a fallacious argument here. I'm really trying to be as accurate and forthcoming as I can, and I want to look briefly here at my old model that I had whenever I shot my time equilibrium video, the one that has like 400 views. And at rest you have this, and this is supposed to be the same length as that, and whenever delta t goes to infinity with velocity going to c, I had, I realized that I could have a divergence, but there was no like correcting of size difference, but because they stay the same radius, like the radius of this circle and the radius of this circle is always going to be the same and growing together. So that wasn't quite right. Whenever you completely impose it over, it perfectly fits, and you get Einstein's schooner. You get the Chronon schooner. And again, at rest, you just have two line segments perfectly laying flat over each other. And then when the little sliver of delta t appears, you get a tiny little triangle. And then it grows. it's just tiny, and then it grows, and then t shrinks to infinity. So this is a dynamic model for understanding basic like special relativity in 2D, and what it implies for photons is that photons, they're not just outside of time, but the real and the virtual component of time that are fluid or can change. Well, at the speed of light, the real component shrinks to zero, and the virtual component expands to encompass the entire time continuum. And that is how we can understand that there is that photons, that's how we can understand like how weird photons are in experiments. Like, we never can figure them out because they're actually in a virtual connection to all points in time. At least that's what I believe can help understand them. And if nothing else, it's interesting to me. And yeah, sideways here, because I had initially, that's delta t growing, but the actual axis that delta t is growing on is horizontal. That's just a tiny little note. That doesn't change anything. Upcoming subjects, you can pause and read through some of that. Thank you for watching. Let's see here. I hope that I have gone through everything that I needed to get through so that I don't have to make a third part to this, but I hope you enjoyed it, and please subscribe, stay tuned, reach out to me. I need your support. I hope to have some merchandise available soon. I've applied for a trademark on my design for Time Equilibrium. You would have seen it in the intro video, and probably but yeah, I should have some shirts or merchandise available soon. And yes, thank you for your time, and feel free to comment. Let me know what you think, and watch my other videos.